What's up, everyone? This is a video lesson for section 7.4, where we will be evaluating trig functions using sum and difference formulas. All right. Now, these formulas are going to be useful because they will allow us to find exact values for trig functions when we're evaluating with angles that are not specifically related to a 30, 45, or 60-degree reference angle or a quadrantal reference angle. Okay, so let's start with the cosine sum and difference formulas. The reason these are referred to as sum and difference formulas is because we're going to take the angle that we're evaluating, in this case cosine for, and we're going to think of it as the sum or difference of two other angles. And the two angles that we come up with, we want them to be related to a reference angle of 30 degrees, 45 degrees, 60 degrees, or a quadrantal angle. Okay, so the first formula is your difference formula right here. So cosine of an angle alpha subtracted by an angle beta, notice that's equivalent to cosine of the first angle alpha times cosine of the second angle beta, added with sine of the first angle alpha times sine of the second angle beta. And then your second formula is the sum formula. Notice it's pretty much the same as your difference formula, except now you have subtraction in between cosine alpha, cosine beta, and sine alpha, sine beta. All right, so let's use one of these formulas to find the exact value of cosine of 15 degrees. All right, now there's multiple ways you can do this. Okay, you basically need to think of 15 degrees as either the sum or difference of two angles that you can evaluate for in an exact form. Okay, so I think the easiest would be to think of this as the cosine of 45 degrees minus 30 degrees. Okay, which means I'm going to be using a difference formula. So applying the formula, this will expand out to cosine of the first angle 45 degrees times cosine of the second angle 30 degrees added with sine of the first angle 45 degrees times sine of the second angle 30 degrees. All right, so evaluate each one of those. Cosine of 45 is radical 2 over 2. Cosine of 30 is radical 3 over 2. Sine of 45 is also radical 2 over 2. And sine of 30 is 1/2. Radical 2 over 2 times radical 3 over 2 gives you radical 6 over 4. Then radical 2 over 2 times 1/2 gives you radical 2 over 4. And then notice we have a common denominator already, so we can combine these into a single fraction. Radical 6 plus radical 2 over 4. Okay? So there's a nice simplified exact value for the cosine of 15 degrees. If you approximate that in your calculator, you should wind up with the same approximation as the calculator would give for the cosine of 15 degrees. Okay. Now, one other thing to draw your attention to, notice what's in green in the top right corner of the screen. You can use these sum and difference formulas with a reciprocal identity to evaluate the secant function as well. Okay, so if I was asked to find the secant of 15 degrees, I would essentially find the cosine of 15 degrees first and then take the reciprocal of it. So that would end up being 4 over the square root of 6 plus the square root of 2, which then, of course, I'd have to rationalize. Okay, moving forward into the sum and difference formulas for the sine function. Okay, notice they look a little different than the cosine sum and difference formulas. Okay, I think the most obvious difference is you're taking sine of the first angle and then now you're multiplying it by cosine of the second angle. Okay, all right, so let's find the exact value of sine of 20 degrees times the cosine of 80 degrees minus the cosine of 20 degrees times the sine of 80 degrees. Okay. Now notice here that that expression follows this format right here. Okay. So that tells me that this could be rewritten as sine of 20 degrees subtracted by 80 degrees. So it's like I'm working backwards here, okay? And then notice that ends up giving us sine of negative 60 degrees, okay? And if we want to evaluate that, that's negative 60 degrees is in the fourth quadrant, right? So we'd have negative radical 3 here, 1 here, 2 here, and sine of that is going to just be negative radical 3 over 2. Okay. Once again, notice that what's in green here, you can use these formulas along with the reciprocal identity to evaluate your cosecant function as well. Right? All right, now we move to the sum and difference formulas for tangent. All right, and these are a little bit different than they were for cosine and sine. Notice they involve some fractions this time. Okay, so let's find an exact value for the tangent of 345 degrees using one of these formulas. Once again, multiple ways you could break up 345 degrees. I think an obvious would be thinking of it as 300 degrees added with 45 degrees. 300 degrees has a 60-degree reference angle associated with it, and then 45 degrees is, of course, its own special triangle, okay? So I'm thinking of this as the sum of two angles, so I'm going to be utilizing this sum formula. So it's going to equal the tangent of my first angle, 300 degrees, plus the tangent of my second angle, 45 degrees, all over 1 minus tangent of 300 degrees times the tangent of 45 degrees. Okay. All right, so tangent of 300 degrees. Again, that has a 60-degree reference angle associated with it. Tangent for that would be negative radical 3. Okay. Tangent of 45 degrees is 1. And then notice it's the same two values that need substituted in the denominator. This time they're multiplying one another. All right, so I end up with negative radical 3 plus 1 all over 1 plus radical 3. And then I'm going to rationalize that. I'm going to multiply by the conjugate of the denominator as a clever form of 1. Okay. All right, so that's going to lead me to negative radical 3 plus 3 plus 1 minus radical 3 up in the numerator. And then in the denominator, 1 minus 3. And then we, of course, simplify. We'll end up with 4 minus 2 radical 3 over negative 2. And then we're going to divide out a negative 2 from everything. So that's going to lead us to negative 2 plus the square root of 3. Okay, so tangent of 345 degrees has an exact value of negative 2 plus radical 3, which of course you can again check on your calculator with approximations, okay? Also, one more time, notice the reciprocal identity for tangent function can be used with these formulas to evaluate cotangent functions as well, okay? All right, one final example here, and this is involving an identity that we have to establish, okay? We want to show that the cosine of the angle pi over 2 added with any angle theta is always equal to the negative of the sine of that same angle theta, okay? So I'm going to start with the left side here, cosine of pi over 2 plus theta. And the first thing I really want to make sure that we never do, I see my students do this all the time, they try to distribute cosine in like it's a number and say that that's equivalent to cosine of pi over 2 plus cosine of theta. Understand, the distributive property only works for numbers. Cosine itself, this right here, this is not a number. It's a function, okay? So you cannot use the distributive property here, all right? Instead, what we have to recognize is that you can apply a sum formula for cosine here, all right? So cosine of pi over 2 plus theta, that's equivalent to cosine of pi over 2 times the cosine of theta subtracted by the sine of pi over 2 times the sine of theta, okay? And cosine of pi over 2 and sine of pi over 2, they can both be evaluated, right? Pi over 2 is a quadrantal angle on the unit circle. It would place you right here at the point 0, 1. So cosine of pi over 2 is equal to 0. And then sine of pi over 2 is equal to 1. So of course, 0 times cosine of theta is equal to 0, and negative 1 times sine of theta is equal to the negative sine of theta. So in the end, notice we simplify to the negative sine of theta. Identity has been verified.